Hey, hey, hey. What's going on, y'all? What's going on? All right. Online. We're still good online? All right. Perfect. All right, y'all. Thank you for coming to another Dallas Software Developer Meetup. I'm Danny Thompson. I'm one of the organizers for this event. We have two other organizers with us tonight. We have Eric over there, and we have Dennis, both volunteers, help out a lot. We also have several organizers behind the scene. Shout out to Clint, who I'm not sure if he's here or not. Oh, there he is. I was like, I thought I saw him, but then I was like, maybe my eyes are playing with me. We have Clint over there. We have Michelle in the background, Melissa, a bunch of people kind of helping out. But this is a community event. If you've never been to a DSD meetup before, kind of give you a background about this. It is completely a volunteer-run thing that we do. We do it strictly for the community. We try to bring as many people together as we can. Honestly, we do a lot of stuff for the community. We do meetups, workshops. We also do something called cohorts, which we're going to kind of go over a little bit in a moment. But obviously, we don't take any money for any of our meetups. We just do it for, honestly, the betterment of the community, trying to bring people together over tech. And so two big shout outs that I want to do real fast. First shout out of the night always goes to our favorite, AppWrite. AppWrite is an open source tool. It's a backend as a service. They are the reason why we have the pizza and drinks. And no matter how big or small our order gets, they never bat an eye at it. Can y'all hear me in the back? I'm pretty loud naturally. If you listen close, you'll hear me. But so AppWrite, anytime our pizza order gets big or small, they never bat an eye at it. So big shout out. If we can get a round of applause for AppWrite, they're the reason why we got a pizza tonight. Second big sponsor of the night, Yum Brands, the building that we're in. They give us this space for free. They don't charge us anything for it, and they let us come twice a month and bring the community out together. So please, huge shout out to Yum Brands. Thank you very much for having us here. Now, this is the first time we're trialing this out. I don't know if this is going to go well or not. We're going to be mindful of the chat on this one just to make sure. But even though, we're volunteer ran, we don't make any money off of this. We spend it like we do. So I bought some wireless mics, and right now it's only set up for the computer. Maybe one day we'll have it set up for this. But online, hopefully they can hear us really well. And I'm going to keep monitoring that throughout the night. So hopefully when we have recordings of our meetups, we try to make sure it's not like a webcam thrown in the side of the room and forgotten about. We try to make sure our online experience is as good as the in-person experience. And the people online right now, I think we're nearing 100 people attending online, give or take. And so with that, there's networking on there, they're hanging out, they're talking, they're geeking out as well. So we try to make sure that anything that we do technically is accessible to anyone, whether they're in our local area or not. So we try to make sure we bring the entire community together and that we're not hiding any information from anybody. Leading to our main presentation with Patrick here from Netflix. And to give you an idea about that, he's a machine learning architect at Netflix, and he's going to talk about how you can use AI to create your first computer vision application.
All right, can everyone hear me? No echo in the back? Thank you. Appreciate the thumbs. All right, thanks everyone for coming. My name is Patrick. I'm going to talk to you tonight a little about computer vision. Before that, though, let's get another round of applause for all the cohort volunteers and participants. Those were some awesome demos. I feel like whoever built the face recognition could come up and give this talk right after me. So I might put you on the spot at the end. Watch out. Yeah, so this subject is really close. I've been a huge fan of computer vision since the very early days of my programming. And we have a little bit of a problem, y'all. We're already getting started a little bit, and I wanted to make this talk like an hour and a half long. I'm not actually going to make it an hour and a half long. We're not going to have to sit through all that. But I am going to have to speed through a couple parts here. And this link right here, the bit.ly intro-2-CV, is the link to the deck if you want to go through at your own pace, walk through everything a little bit later. Highly recommend that. I can also put it up at the end or maybe throw it in the Discord or something so people have it. But we're trying to cram like 3 years roughly of learning into a little less than an hour. So we're going to be moving right along. Don't feel bad if you need to kind of go back over things and take another look. And feel free to stop me and ask questions along the way if there's anything you want to spend a little more time on. But to get to why I care about computer vision, you'll have to indulge me in a little bit of a personal story. And it starts with a video game in the middle school. RuneScape, for those of you that may be familiar. It was an online role-playing game. In this game, like many role-playing games, You go on quests, you collect gold, you get items. And back when I played, this game was popular enough that there was a black market in the real world for items in this game. So, oh, sorry. Yes, I can do that. Man, ruining my RuneScape momentum here. Okay. Good online? All right. Sorry, everything. Where was I? Black markets. Yes. So if you had like 1 million gold in this game, that was like $7 or $8 in the real world. Depending on how good you were, you could do that in about 4 to 8 hours. So as a poor kid, $1 to $2 an hour to play a game sounded pretty amazing. Even better if I could figure out how to automate doing that while I was in school, which of course I tried to do. So in order to earn this gold, you got to click on something in your inventory, click on something in the game, go do something else, click again. And if you've ever done UI automation, it's pretty straightforward if everything's very well labeled and stable and looks the same from iteration to iteration. But unfortunately, the makers of this game knew that people were trying to automate it, didn't want people to automate it, and tried to make it a lot harder. So they would randomize stuff that happened in this game to try and throw you off. So while right now this kind of blow up is a particular blue color, the next time you played the game, it might be, oh, hold on, sorry. It might be a completely different color that's just lighter blue, slightly different. And if you tried to withdraw it to your inventory, it wouldn't go to the first slot, it would go to a random slot. And so you would have to do things like scanning all of your inventory slots looking for a particular color. Long story short, you can't automate this with a bunch of rules. You have to do this like a person does and recognize, hey, this object looks kind of like a circle with some blue, and recognize it like a person does. And that needs computer vision. So that started my entire journey into programming and computer vision all the way back when. So whether that story impressed you with my skill or depressed you with my lack of friends in middle school, thankfully I've improved a little bit of both since then. Some of my favorite achievements since then, if you've heard of Lighthouse, I worked on Lighthouse at Google with Paul Irish, who's one of the creators of jQuery, if you're old enough for that to mean something to you. After Chrome, I started a computer vision startup that got acquired in 2021, and then now I'm an ML architect at Netflix, where I work on visual effects and AI for Netflix Studios, which we'll get to in just a minute. This is also where I stop and say, I am not representing like official Netflix something here. I'm just a guy talking about computer vision that I like. The Netflix color scheme is just because I drink the Kool-Aid, and I think what we do is really, really awesome, and we happen to be hiring. So if you are interested, feel free to come up and talk to me after this. Shoot me an email, LinkedIn, whatever you're comfortable with. But I don't want to hear anyone on Twitter like, well, Netflix told me, blah, blah, blah. No. This is just Patrick talking about computer vision. And this is what we'll talk about today. We're going to do a quick overview of just what does AI at Netflix look like? What do I do? Kind of ground what we're going to learn in some actual business value. And then we're going to walk through a crash course in AI and machine learning and computer vision and media APIs. So like I said, there's a lot we're going to run through. If you're totally lost, please feel free to stop me, ask some questions. At the same time, it's condensing 3 years of info into less than an hour. If it's way over your head, stop and ask. On the flip side, it's going to simplify a lot of things. So if you already know a lot about AI and ML, please feel free to interject, add some extra perspective, help those around you who seem confused, right? This is a community event trying to make everyone better. So help me out when, if you already know what's going on. And then at the very end, we're going to put it all together and have an actual application. I will whiz through a lot of this stuff. So first up, AI at Netflix. What do I do? What happens? Well, Netflix's mission is to entertain the world, or at least these bright red parts of it. That's super cheesy, really broad, doesn't really tell you anything about machine learning, but it's the mission, so I got to throw it in here. More interesting are these 3 buckets of kind of AI and machine learning that I think Netflix does particularly well. The first one is really generic, what pretty much every single big company on the planet does. It's data science and business intelligence. It's doing things like, do our customers like us? How much do they like us? Do they like us more than our competitors? Should we invest in this product? answering those types of questions with a lot of data. This next bucket is for content recommendations, and this is what Netflix sort of became famous for about 10 years ago. They threw a lot of money at famous conferences and papers and research, trying to make sure that the right content got recommended to the right person at the right time. And this bucket is anything that is taking a look at what you have liked watching in the past and trying to predict something that you haven't seen that you might be interested in. So obviously, very important for Netflix, and a lot of investment has gone into this particular area. What I work on, though, and what I'm personally most excited by is this bucket of content creation and the creative production process. So this is any use of AI or machine learning that tries to help creators and storytellers tell better, more engaging stories and create better content. So that can be really advanced things, trying to make it possible to tell stories that have never been told before with really advanced visual effects, or it could be things like just making sure artists get to spend more time on the creative parts of their job and less on the mundane, very repetitive tasks. But even just this creative production process is super broad. So this is a dim picture that'll get a little brighter in a second of the entire process of kind of someone thinks of an idea for a TV show or movie to the time that it actually gets to something that someone can watch. So this is one of the things we're gonna whirl through. None of this is secret. You can kind of Google, this is a general Hollywood process here. So if any of these particular stages sound confusing or interesting to you, feel free to just look up that specific type. But start with a pitch. Someone has an idea. They go to someone to get some money to make it. Right? They have maybe a screenplay and some idea of who might be interested in building it. They move then into something called pre-production, where they're maybe planning out what this is going to look like. They're figuring out where they need to go, where they need to film, who's going to help, and when. Then they move into actually being on set. This is kind of stereotypical backlot Hollywood. They're filming every day. They're reviewing footage. The movie's starting to come together. Then they move from the set into basically a room full of computers where they're doing editing, they're doing visual effects, post-production, sound design, computer graphics, anything that is kind of big and flashy to round out film. And then when they've got sort of a rough cut, they move into localization where they're doing subtitles and dubbing and maybe testing it with some local viewers. And they're trying to actually promote it, tell everyone about this. They're making trailers, hero art, posters, billboards, all the associated media that's going to go along to actually let people know that this is a movie. And then they actually need to get it to you, right? So in Netflix's case, this means transcoding it, uploading it to a bunch of CDNs, making sure that, sit down and hit play, it's ready to go. And my team and what I'm responsible for is this white box here for any sort of AI, ML in the pre-production, production, or post-production across live action movies and games. And some concrete examples, these are ones I'm gonna whirl through, but there's individual blog posts about each of these projects on the Netflix tech blog if you're interested. We've invented new green screen techniques, can predict when scenes change, and have editing tools to help create kind of trailers with match cuts, which is that cutting between different videos that have similar structure but different content. So again, if this sounds interesting to you, this is the whirlwind of AI at Netflix. Please feel free to come up with me after, chat, shoot me an email, LinkedIn, whatever. I think what we do is really, really awesome, and it'd be awesome to work with you. But now let's get into the meat. AI and machine learning, what is it? We're going to do a real high-level crash course just so you understand what's going on underneath the covers of this very important topic for our time. And I'm going to start with a definition of AI that I particularly like, and that's anything that machines can do that we used to think only people could do. And I think that this previously thought is an important component because how we define AI has changed over time. And things we used to consider AI are now just, well, of course, machines can do that. We don't really think of it as AI anymore. So while today we think about ChatGPT and Midjourney and Stable Diffusion, maybe the Terminator as AI, the original AI was literally just random numbers. And I'm not even joking. One of the first things you learn in machine learning and AI type of classes is Monte Carlo research, which is sort of the foundation of many board game playing AIs. And all it's doing is playing completely random moves over and over and over, and then counting which one wins the most. And this was state-of-the-art AI, and in fact is still been used quite recently as some of the best game-playing artificial intelligence out there. And it's just random numbers. So, and from 3 to 8 years, you will have a machine, the general intelligence of average human being. Marvin Minsky said this, who founded MIT's AI lab in 1970. So clearly what we think AI is and what level of intelligence it needs to achieve has changed a little bit in 54 years or so. Because even people that say that sentence today are, let's see. So that's AI. Machine learning, generally used interchangeably today, and that's largely fine if you want to do that. You're not terribly wrong most days today. But I like to separate them as, if AI is this class of problem that machines can do, that we used to think only people could do, machine learning is a very common technique to actually solve those problems. So it's a very specific strategy that you use in artificial intelligence to try and achieve some of these things. And the strategy is get lots and lots of data and have the machine learn how to solve that problem from the data rather than giving it very specific instructions. So when I first started getting into machine learning, what it felt like to me is I'm writing like 1 million test cases and never getting to write the implementation, which if that sounds terrible. I thought it sounded terrible at first, but there ends up being a lot of cool things that you get to do around the edges of machine learning as well. So some core concepts you need to know. If you are here, which means you're interested in tech, and you've been alive in the past year or two, you might have heard the word model at some point. But what exactly is a model? Well, a model is really just a description of how to process some data in order to get some useful other data. And there's 2 key components that I want you to take away from what a model is. There's the generic procedure that you apply when you're running your model. And then there's specific numbers that you're going to use in that procedure that are called parameters. So this general process or procedure that you're going to run, often called the architecture. I'm going to use procedure because I think it's generally helpful if you don't have an AI background to think of it as a series of steps that you're going to take. And then there's the actual numbers you're going to use in that process. So as a concrete example, we have a super simple model here that's really just multiplying input by 2, adding 4, and then dividing by 3. So the procedure or architecture here is basically this function where we're going to say x times some parameter plus some other parameter divided by some other parameter equals our output. And our parameters here are 2, 4, and 3. That's a model. Pretty simple. We have 3 parameters, fairly easy to follow. You might think, well, I don't need machine learning for that. It's just like a plus sign and a multiplication, division. But you can also have really crazy models like GPT-4, which have probably a lot of words that you don't even know what they mean, and that's totally fine. Self-attention, positional encoding, regularization, skip connections, feed-forward networks. That's a different type of procedure that you can apply to a bunch of data. And the number of numbers that you need in the series of steps is much, much bigger than 3. It's roughly 1.7 trillion. So when we say large language models, we mean really large, like terabytes of data. Now, you might be thinking, well, how do I get those numbers? Like, it's not like they have an army of people deciding, well, parameter 7,843 is going to be like 0.3. That's where the machine learning part comes in, right? So what you do as an engineer or as a machine learning practitioner is defining the procedure. You define the model architecture. You say, I think we're going to transform our data in this way, but I don't know the parameters. And the process of getting those parameters is called training. So taking our model A example, right, our general process that we said is going to be multiply the input by something, add something, and then divide by something. So that's what we as the engineer get to decide. And then we hand that description plus a ton of examples to a machine, and it decides what the question marks are. It decides the parameters and figures those out in a way that would make sure that this function generally matches the data that it was given. And this whole process of figuring out those parameters is what training is. But at this point, we haven't actually achieved anything. All of the data we had, we already knew the answer, right? For every single X, we already knew the Y that it corresponded to. And just having a model sit there doesn't actually help us do anything. So the last big concept that I want you to take away is inference, which is the actual using of a model to do something useful. So inference is when you take a model and some data you haven't seen before, and you predict what the output's going to be. So in our model A case, it's here's my function, and here is a specific X value. Can you please give me Y? So a quick recap of 3 core concepts. There's a model, which is just a procedure transforming some data along with some parameters. There's training, which is the process of figuring out those parameters. And then there's inference, which is the process of applying all of this to some new data. So procedure and parameters, figuring out the parameters, actually using everything on some new data. And when you're doing all of these concepts, you're going to run into a couple of the same problems over and over and over again. The first 2, tightly related, it's how do you represent your input and your output? Computers are pretty good working with numbers. So if you have a numeric problem, like say predicting housing prices, you're pretty much good. You don't have to think about these questions too much, right? Your house price, that's a number. Your input's probably something like square footage, lot size, number of bedrooms, number of bathrooms. All those are numbers. You don't really have to do very much. If you have something a little more complicated, though, like a novel or a bunch of text or an image or a video, you have a little bit more work to do to figure out how you're going to represent your input and your output. The other big question that if you are in machine learning or AI at all, you spend almost all of your time doing is the data question. How do you get the training data? How do you clean the training data? How do you validate that it's accurate? How do you make sure it's free of bias or discrimination, or it's balanced to actually represent the problem you're trying to solve? The vast majority of people in ML mostly answer this question about whatever problem they're working on. The last one that's a little flashier is the architecture question, or how are you going to allow the model to transform your data? And in our model, this is corresponding to what sentence, what description are we going to give to the computer during training to allow it to learn the right parameters. And the short answer is you don't have to care about this problem yet. The vast majority of people in ML aren't coming up with brand new answers to this question. The field is sort of narrowing in terms of the organizations that can conduct large amounts of research in this, and they require a ton of GPUs, an enormous amount of resources, a lot of expertise. So unless you have a PhD or have done this for a very long time, you're probably not going to come up with brand new ideas on how to tackle this architecture question, and that is completely fine. I have not meaningfully contributed to this question ever in any project I've undertaken, and there's plenty of space for you in AI and machine learning answering these first 3, I promise you. So don't let the description of whatever GPT-4 does and not knowing what that is intimidate you in any way in terms of getting into this space. So I want to walk through a specific example, and we have some input and output data here. Before I go, does anyone want to guess what this data is? This is some real data from a real data set. Be brave out there.
Video.
Video? Not video. What if I told you that the input was in inches? Oh, here's some murmuring. Anyone brave want to raise their hand? Anyone online? All right, it's inches, and then output is weight in pounds. So these are heights and weights of people. So these are both numeric. We're going to try and come up with a hypothetical model here that's going to predict someone's weight given just their height. Anyone want to take a guess how we're going to represent our input? This is it. This is a softball. This is an easy one. Yes. Yeah, it's just going to be a number. Just a number. What about our output? How are we representing our output? Yeah, just a number. The easiest questions you'll get to. How do we obtain our data? Well, you could go around to your friends and say, how much do you weigh? How tall are you? Write it all down and then throw it in here. Wouldn't highly recommend that approach, but something you could do. You could also go and just try and find some data sets online of a study that's been done. Whatever you do, don't make it up. Try and get some sort of real world measurement that actually reflects the problem you're solving and the data you're trying to get. And then this last question, how do we enable the model to transform the data? So I think the earlier answer was getting close to this. I'll take a stab. Yeah. Yes, the response was you have to train the model first so I can figure out the parameters. That's exactly right. For our model, we need to define what the function is going to be, what the procedure is going to be. So the general stab you can take at this is come up with some hypothesis about how the input and output are related and try it out and see how it goes. In our case, we're going to say, let's imagine you have some fixed amount of weight that gets added for every inch, and we can represent this as a linear function, basically, a linear coefficient offset. So our three main concepts, right? Training is going to be, hey, computer, here's all my input numbers. Here's all my output numbers. Please figure out my two parameter numbers. The model is going to be something like output equals input times parameter 1 plus parameter 2. And parameter 1 is 12.5, and parameter 2 is negative 700. Which implies some weird stuff, like every inch you gain 12 pounds, and a person of 0 height is negative 700 pounds. These problems are sort of beyond the scope of Crash Course, but if you're intrigued by this, I encourage you to follow up and do a little more research on how you can get around some of these and what they mean and apply. And then inference is going to be a process of actually running someone's height through that. And that's it. That's everything really basic that you need to know about AI and ML to move on to computer vision. So what is computer vision? Computer vision is sort of a subset of AI that specifically deals with the processing and understanding of visual information, right? It's literally giving a computer some sort of vision about the world. And there's a couple of main basic tasks that come up a lot in computer vision. The simplest one is just classification. So that's like showing someone a picture and saying, describe in one word what this picture is. That's classification. So here, what's that? It's a cat. That's all you get to do. Detection is a little more sophisticated. It's like saying, where are the cats in this picture? In this case, we've got bounding boxes of human faces where you get sort of coordinates and then a relative size of each object of interest. And then if you step up even further, you get something like segmentation, which is not just boxes of objects, but labels for every single pixel in the image, what it is and what it belongs to. So this is self-driving car example where you really want to know what's a road sign, where's the pedestrian, where are the road lines, where are other cars, and you don't just want general boxes of this. You want to know exactly where everything is. And we have the same core problems that we have for all machine learning and AI tasks. Input representation is a little more complex now, right? We don't just have a single number as our input. We have video or an image. So what is an image? If you've been around image codecs or any sort of manipulation of images, you might be familiar with the concept that an image is just a three-dimensional array of numbers. It's just a bunch of pixels. How many people are kind of loosely familiar that RGB is like a thing for images? Okay, maybe 50%. Okay, cool. So if you break down an image, it's a bunch of tiny dots of color. Each one of those is a pixel. And the first two dimensions should be fairly straightforward. It's width and height. And then this third dimension that we have is called channel, which is breaking down the intensity of red, green, and blue light in every single dot of color. So if you've ever messed around with kind of settings on your TV or your monitor, you've usually been messing with something to do with the RGB channels of images. And each one of those is represented just as a number of 0 to 255, which is just an 8-bit integer. So if you've ever used CSS, and you've specified a color with, hash 0FCDAB. Each one of those 2 characters is a hexadecimal integer of between 0 and 255, specifying the red, green, and blue channel. So that's what you're actually doing, specifying those. And a video is just a series of images, right? So frames per second is the number of images that get shown per second to create a video. Videos are just the illusion of motion through changes in pictures. 24 frames per second is sort of Hollywood film standard. And if you're a gamer, maybe 60 FPS is like the minimum that you'll tolerate, gold standard, which makes a video just a 4-dimensional array of pixels, right? We got width, height, channel, and now we have time or frame number. So we got our input down. We figured out how we're going to represent. Output still can be a little tricky. It depends a lot on the problem that you're solving. If you've seen Silicon Valley, you might be familiar with binary classification, in which there's a funny miscommunication when someone thought there was a magical AI app that could tell you what any food is, and all it can tell you is that a hot dog, yes or no? So that's binary classification. So in that case, your output is just a Boolean, right? 1 if it's a hot dog, and 0 if it's not. But you also have slightly more complicated questions you can ask, like where is the hot dog inside this image? In which case, you not really have a Boolean anymore, right? We got this whole box around our hot dog, in which case we need at least like 4 numbers, right? And maybe X, Y, where it starts, and then another width and height within it. And if we want to detect like, I don't know, 500 hot dogs, right? Then we need 4 times 500. So, 2,000 numbers reflected in our output. So this is going to change depending on, but you want to find a way to numerically express whatever your output is going to be. So we've done input output. Last big question is architecture. And I said you wouldn't have to worry about this too much, but I think it's important to just understand what's going on under the hood. And the good news is you don't need to invent these. You just need to kind of look around at the problem you're solving, find someone who's done it in a particular way, and use that architecture that's suited to your problem. Sort of like when you're making a table in a web app, you're not reinventing a brand new way to sort things. You're just using a sort, and you're leveraging that sort to complete your app, right? Same concept here for architecture. And the main term that you may have heard, need to know about, is a neural network. So a neural network is a type of model architecture that mimics how the human brain processes information. And the way it looks is something like this. This is a very simple neural network where each one of these circles here is a neuron. And each one of these lines is a connection or weight between neurons. And every single one of these lines is a parameter in our model. So usually each node here is like a weighted average of some nodes in the previous layer. And they're organized into these layers where the first one is all of our input, and this output layer is however you decided to structure your output. So the input layer is going to be all of our pixels, all of our individual numbers for each pixel. And this output layer in binary classification would just be like a single node, right? If it's 1, that means it's a hot dog. And if it's 0, that means it's not a hot dog. And all of these layers in between are called hidden layers. And the intuition here is if you start with really raw, low-level information, like the red intensity at this particular dot is 55, and then you end up with a really high-level answer, like this is a hot dog, then as you go through the network, you're developing higher-level understanding of what's going on with your input, right? So if you have a classifier for, say, the cat image, when you start, you might be answering questions like, is this a cluster of things that looks like a line? And when you get to the very end, you might be saying things like, does it have pointy ears? Does it have a tail? Does it have 4 legs? As you move forward through the network, you're extracting higher level information as you go. One last thing I want to note about the neural network architecture. So this is a densely connected layer where you can see there's a line between every single node. There's a lot of crisscrossing going on. This gets really expensive really, really fast. If you had like a 1 megapixel image and 7 layers and everything was densely connected like that, you would end up with 7 trillion parameters to learn, which is way bigger than even the largest large language models. So we need to do something here to kind of limit the intensity of parameters to make this a little more efficient overall. And for that, we're going to rely on something that's just from regular image processing, has nothing to do with AI, as long outstanding before that, and that's called convolution, which is just a technique in image processing to replace some individual pixel values or points of color in an image using the information around it. So not just its own value, but something. To make it concrete, you can do 2 simple operations using convolution. The first one is blur. So a blurry image is just a sharp image that has its differences averaged out a little bit. It's kind of smoothed. And to do that with convolution, you use what's called a convolution kernel, which is just this 3x3 matrix here. And you convolve the image, which means you take this matrix and you look at every single pixel in the image and you apply it, which is just a weighted average here on every single pixel to get the output value. So this is one of the harder steps in the talk. So if it's glazing over you, no worries. We can come back to it, spend some extra time, look it up separately. This bottom example, I think, is a little easier to understand, where this is shifting the entire image to the left 1 pixel. And in order to do that, that pixel there is just being replaced by the value 1 pixel to the right. So whereas in the top, we are adding all the pixels surrounding it and then averaging them, here all we're doing is replace every pixel with a pixel to the right. Everything else is 0. And then what that does in the end is shift the entire image to the left. So you don't need to understand the slide in particular. The most important thing is you understand it's not trying to use the information from the entire image to change each individual pixel. It's just using the information of pixels around it. And so when you combine these 2 concepts, neural networks, convolution, you get something called a convolutional neural network, which is a neural network, but instead of every single neuron being connected to every single other neuron, the neurons that are connected are just the ones that are around each other in that image. And to make that a little more concrete, what that looks like is you might have a kernel that moves across this zebra's leg. And at first you're learning things like, are there vertical or horizontal lines? Are there dots? The next hidden layer, higher level information, is this stripes? Is this just a really big line? And by the time you get to the end, you're learning things like, does it have 4 legs? Does it have a tail? Does it have a striped body? And that eventually gets you to the final answer of, is this a zebra? I'm going to take a deep breath. We're almost there. I know it's long. So this is the media APIs crash course. We're through machine learning. We're through computer vision. We got our basics down. Now we're going to actually try and make use of some of this in JavaScript in an interactive web app. We're going to start with navigator.media devices, which is a collection of APIs that gives us access to the webcam, microphones, displays, things like that. And this is pretty simple. We're going to have a few lines here. We're going to ask the browser to give us 720p video, in this case with audio. And we're using async await because we need to ask the user's permission. You can't just like activate their webcam sneakily without their permission. And then we're going to attach that to a video object so we can see it. And with just this like 4 lines of code, you actually have a complete webcam viewer running in your browser. So you don't need much more than this. You know, I'm missing a few lines of HTML here, but this is the gist of all you need to get a real functioning webcam display. Where were the pixels, right? In order to do all the things we've been talking about, right, we needed pixels, and this was just an opaque stream object. Well, in order to get some pixels, we need the canvas element. Canvas element is a really low-level API in browsers that lets you get kind of graphics access of controlling the individual value of every single pixel, right? So normally when we work with the DOM and browsers in general, we maybe put a span or a div, and we throw some text in there, and then it just renders everything nicely for us. Canvas is where you get to say, all right, put black dot there, and then a red dot right next to it, and then a blue dot right below it, and you can draw whatever you want. And the way we can manipulate all of these individual pixel values is there is a put image data, which just is, hey, I'm giving you a ton of pixels, put them at this coordinates, and you can also get image data out of a canvas to read back what you've written. And the only caveat here, I've been talking about 3-dimensional arrays. uint8 array is a type in JavaScript that Canvas uses for all of this, and it actually flattens everything. So I know there's a lot of complexity going on here. I'm going to add one more, where instead of the 3 dimensions, it is just in a single array of R, then G, then B for the first pixel, then R, then G, then B for the next pixel, then R, then G, then B for the next pixel, instead of being 3 separate arrays of images. And then when you get to the end of a row, you just keep going instead of starting a array. So with that, you put it all together, you get something like this, where you can draw what you got from get user media onto a canvas, and then get out the image data as pixels and start actually doing something interesting. And so what are we going to do with it? Well, we're going to use something that's going to do all the heavy lifting that makes most of this talk not necessary for you, but I think it was helpful to understand what's going on. MediaPipe Task Vision is going to implement all of the model for us. It just has a nice handy API to pass in some pixels and a canvas element, and it kind of does the rest. And this is a little more complicated. I have code links at the end, so don't feel like you have to jot all this down. But basically all we're doing here is importing this NPM package. We're extracting some of the classes from it. We're passing a path to a particular model that we're going to use from this package, which is called face landmarker, which is going to give you basically a mesh of your entire face that it detects in the image. And then we're passing it an image to actually go and work its magic. And so you end up with something that looks like this. A little blurry, but it's a mesh of all the different points on someone's face that it detected. Does anyone want to guess, what does the output representation look like for something like this? What do you think it's returning to you to get this sort of information? Yeah.
Thinking it might have a number that represents a place, a dot, and then another number represent how that was being realized. Or...
Yeah, you're definitely on the right track. There's at least one number for every point on this mesh. And the way it's being returned to you is they basically have a list where they say the first 2 numbers I'm giving to you are like the nose, and it's just the XY coordinate in the image for the nose point, right? And there's about 400 points on this mesh where they just have a convention where they say, well, the first one's the nose, the next one's the eye, the next one's the mouth, the next one's the dot next to it. And they have a label for every single one of these points on the face. And every single one is 2 numbers, right? The X and the Y coordinate within the image of where it is. So it's about 800 numbers is the response that you get. And that's the crash course on media. So we are like 2 minutes away. This is great. No questions the whole time. I'm flabbergasted. Building a computer vision application, actually putting all of this together. So we had our 4 core problems, right? Input, what are we going to do? We're going to grab it from get user media. Output, what are we going to do? We're going to grab the Canvas API, put it out there. And then MediaPipe is going to handle pretty much all of our architecture and data questions, so we don't have to think about it. And we're going to try a live demo. You're welcome to go do this yourself. This kind of puts it all together. Intro to pixel bending.surge.sh. Live demos never go wrong, so might as well try. All right. And the problem, but I can't look at it and do it at the same time. Is it working? Okay, I have to take your word for it. I can't see it. So. Feel free to go there yourself. There's the code example and the slide link on there as well. I cut out all the part where we walk through doing this because I figured 45 minutes of a really dense talk is long enough. So let's... Questions? Thanks, everyone. Appreciate it. Yes. Yeah, so there's a ton out there for Python, which is honestly why I picked JavaScript this time, because I figured for the most part, Python's like pretty well covered out there. So there's plenty out there for Python. There's bindings for a lot of these common libraries in a ton of different languages. In fact, MediaPipe itself is not just JavaScript, but also Python, and I think Java, maybe C++. I don't remember which bindings, but a lot of libraries have multi-language bindings out there. My advice would be to just kind of look for one of the awesome lists on GitHub that's just like awesome ML or awesome computer vision, and look through there for the different kind of like language sections of what's popular. A lot of different ones have multi-language bindings, like TensorFlow is both JavaScript and Python and C++. There's a lot of them that have multiple languages. Yes.
Question. Third stage language. So does the whole model just run on my phone?
Yeah, the whole model's running. Yeah. Yeah, so it's using WASM WebAssembly to run everything on the client.
The model.
Yeah, the whole model.
That's very good.
Yeah, it's great. All right, I have a question for everyone. How many people felt like the content here was like old news? They already figured it all out. A few. Okay. How many felt like it was just went way over your head? This wasn't useful. No one? Okay. I saw someone start. No shame. Okay, so everyone else thought it was exactly perfect. There's no way. Yeah.
People are raising their hand in the chat.
Oh, they are? Okay. All right. Did you get like a rough percentage for me? What was the 3 people? Okay. Oh, other questions on the chat? Sorry, I've not been checking. You're good? Okay. Anyone else? Any questions? Yes. That I am specifically solving, unfortunately, no. They're fairly secret, so I won't answer those directly. But the Netflix tech blog has a good example of general projects that are public knowledge that my neighboring teams are addressing right now. So I would definitely recommend checking those. The magenta green screen, scene detection, and match cuts are some good examples. There's some also interesting ones on the promotion side that have been published recently. So not the kind of pre-production, production, and post-production box that I work in, but the promotional media where they're making like trailers and media.
Patrick,
yes.
That you know nothing. You want to start for AI. What is the next step? The first step. Yeah, so I always recommend picking a concrete project or something that you want to exist in the world. Like the cohort example of the face recognition is a perfect example of taking something realistic and just learning everything you need to make that real. And so that'll get you started with kind of what we looked at today with MediaPipe and using a model and figuring out what input it needs. Once you're comfortable with using a model, then you can work on, well, how can I make one? And you already know some of the basic concepts right involved of actually using all of this stuff. So there's also plenty of courses. Andrew Ng has a company that's just like dedicated to deep learning. I think it's called deeplearning.ai or something similar. They're really good, high quality ones. I think I started on one of Andrew Ng's Stanford courses a really long time ago, but on Coursera back when it was just kind of openly available. So pick a project, something concrete that you need to build, learn everything you need to make that real, and supplement with courses along the way to figure out what you need to. Yes. So for the ones that you heard before, you gave a formula, right? And you gave something like input times, time ones. But what about the you didn't give anything to it, right?
Yeah, so that is just it wouldn't fit on the slide, but that is just a really complicated formula, right? It's just saying, we can actually go back to that.
What did you do with the formula?
Yeah, so ultimately, right, the value here is a formula, right? It's this weight times this value, plus this weight times that value, plus this weight times that value, plus this weight times that value, right? And then you got to do substitution. What's this value? Well, it's this weight times this value, this weight times that value, this weight times that value, right? You can trace it back all the way here. So along the way, right, the formula for like y equals x you know, times whatever, for this node is a really long formula of nothing but this input layer and your parameters. Yeah, so that's what like all these libraries are for, is expressing, you get to say, I want a network with 5 layers and 5 nodes, and it's like 6 lines of code. Under the hood, the library is saying, okay, I need to create a giant formula of all of these parameters and weights, right? So, you know, 8 years ago even, right? Like it was very painful, right, to do this sort of thing, because there was not as much kind of syntactic sugar to do a lot of this stuff. But now if you use, you know, PyTorch or TensorFlow or a lot of the libraries out there, you basically say, I want a neural network with 4 layers and 2 hidden layers of 5 nodes, and it's, you know, 4 lines, and then you've defined your model architecture and you're done.
I want to do 4 layers of 5. What goes into that?
Yeah, so that's what I was referring to with the contributions to answering that question are usually done at this point, largely by PhDs with a lot of experience in a lab. And you are mostly going to be looking at what's called a model card of someone else that's already done this and saying, I'm going to copy that and use that architecture. So for the most part, you're not reinventing the wheel at this point. Most problems that you see are going to be, you know, look, I really like the sort analogy, right? When you're sorting stuff in a table, you know, like, man, I need to invent a new sort. Like quick sort and heap sort and all these things are just not good enough. Like you can use one of them and you'll be just fine, right? You can focus on your specific problem. So this is where sometimes you might need to read like an academic paper to understand like what network shape you should be using. But at this point, there's just lots of content out there for, you know, hey, what network shape should I use for this particular problem? And there's lots of discussion about what it should be and, you know, how to make it better.
Any further questions to be handled after the presentations, get a group photo, and you can approach it after.
Sure. Yeah, I'm sticking around for a while, so feel free to come up to me. Thank you, everyone.